check again. Everyone's got me on full screen. So yeah, welcome to this demonstration of concentration measurement. It's primarily centered around the spectrophotometer, although we'll show you the operation of the refractometer as well. This should be an in-class demonstration, really, but because of the restrictions, that's not possible, and only one person is allowed in each laboratory in the NCMH at the moment. But this is quite fun doing it online. We've had some fun already, actually, trying to get the teams to work. But yeah, let's see how we go. Right. So on the Moodle for your modules, there is a file marked concentration measurement demo, and I've also put that on the chat as well. And it consists of two sheets. The first of which, I don't know whether you can see that. Is that reasonably clear?
Yes, it's clear. Okay.
So yeah, the first sheet is just a description of measurements of concentration by spectrophotometer and refractometer, and the second sheet is just an optical diagram of the workings inside of a spectrophotometer. That's mainly for interest, really. So you may wonder how these, what's inside these. Let's try and get that into view. Right. Can you all? Let's get the camera down there. All see my friend, my spectrophotometer. That's the Beckman DU640 spectrophotometer. It's an old one we no longer use. It's been superseded by other ones. So rather than throw old instruments away, what we tend to do is to save them. And they're very useful for, first of all, spare parts, but also for showing showing how they work. So yeah, so the first part is going to be me just showing you the spectrophotometer, what's inside it, and then Thomas MacCalman, former MSc student, now doing PhD, he's going to show you how we measure the concentration of a protein solution, and what to do when readings go outside the Lambert-Beer law, which links the absorbance with the concentration. This is the extinction coefficient at a wavelength lambda. L is the path length of the cuvette, which is typically about typically 1 centimeter. And this is the corresponding equation if we work with molar concentrations, where lowercase c is the molar concentration, and this is the molar extinction coefficient. And since that relation is the same, equivalent to that one, then the molar extinction coefficient is related to the standard extinction coefficient simply by this molecular weight multiplier here. Sometimes people prefer to work in molar concentrations. Sometimes people prefer to work in weight concentrations. So for bovine serum albumin, these are the different values for the extinction coefficients, the standard one, and the molar extinction coefficient. And here's our favorite protein of albumin, and the extinction coefficient 60 mils per gram. So that's what we're going to be looking at now with Thomas. But before I do that, I thought I'd just show you just inside one of these instruments. I'm just going to shuffle this around. Well, basically, before I do that, this is what normally opens, and you put your sample in a special holder inside the sample chamber here, making sure that you have the clear part of the cuvette in the light beam, not the frosted part here. The frosted part at the top and the side are designed for you to grip. You do not grip the faces of the cuvette where the light beam goes through, because any smudges and things, you've got proteins on your fingers, that will cause erroneous results. Let's just juxtaposition this round a little bit and then move. Okay. Right, I'm going to take the lid off. Again, I'm assuming you can see that. I've got this tiny screen here, which indicates what you can see. Let's get rid of the lid. Right. Okay. I don't know what you. Just checking what you can see on the camera here, because it's very, very small. Right, can you see the inside of the spectrophotometer here? Is that all clear on your screens?
Yeah.
Okay. Right. Just turn that a bit so you get the light source. So what you basically have is, let's get a pen. Right, so I'll just take this out here. Right, I don't know if you can see that. Let's turn that around a little bit. Can you see where my pen is pointing? You can
now.
Okay, so basically we've got two light sources here. Maybe I could put the room light on so you can see more clearly. Okay, so you've got basically in there, that's a tungsten light source. That's for dealing with wavelengths in the visible, really, wavelengths greater than 350 nanometers. And this larger light source here is called a deuterium light source. And this is for really looking at wavelengths in the ultraviolet. So for protein work around 280 nanometers, we would use the Deuterium lamp. So two lamps, one for visible mainly, and one for ultraviolet work. That's all encased in there. Right, now let's just twist that round a little bit, just to adjust that down a little. So if you were all gathered around here, we'd all see this very, very clearly. So this is having to substitute for that. Let me just check if you can see those mirrors. Again, it's difficult to say on my tiny screen whether you can see this. But right. So basically, you've got your two lamps inside here, and depending on what wavelength you choose on the settings, or if you're doing a scan, then there'll be a mirror which diverts light either from the tungsten light source or from the deuterium light source coming out of this point here. Just shout if you can't see anything, okay? That means you can unmute, folks. I don't mind you being unmuted here. And then the light beam goes through this, what's called a source mirror, and then by this transfer mirror, and then through this additional slit here called the entrance slit, and then the light beam traverses to this beautiful optical component here, which is basically a diffraction grating. Can you see that or not? Can you see what I'm pointing to now?
Yes.
Yes. You can. Right. So then, depending on the position of this basically helps to select the wavelength. So the position of this is adjusted depending on what wavelength that you have chosen, obviously working with the appropriate light source. Then if I come around here, then just move around a bit. Can you still see where my pen is, folks?
Yeah, it's clear. Yeah.
So the light goes from the grating through what's called an exit slit, and then this wheel has optional additional filters which you may want to use depending on what you select on the panel, which the control panel where you do the settings, which can be linked to a computer, and then via a filter or not, then through to this. Maybe you can't see this now. Can you see where my pen is pointing now or not?
Yes, I can see that.
Okay, there's a mirror here. This is called transfer mirror, and then eventually to a sample mirror, and then the beam at the appropriate wavelength is diverted through this porthole here. Don't forget, this is all fully closed off, so there's no extraneous light coming in. And then, let's just pick that pen up. Oops, a daisy. Maybe it's best if I just unclip this camera. There we go. All right, so the light goes from the, sorry. Well, let's just recap that. So the light goes from the sample mirror, can you all see down there? Then through this hole, and then light then is basically passes through the sample, which is in the cuvette, and then is recorded by a detector, and then through to a computer which records the absorbance. So that's essentially what you get for a spectrophotometer. There are some variations, of course, depending on the type of spectrophotometer that you have. Some spectrophotometers are double beam, which means you can correct for any absorbances that are in your solvent or buffer. This is a single beam spectrophotometer. And some spectrophotometers have a carousel, so you can get a set of different solutions all ready to go, and then just move either manually or by a control or attach computer to the spectrophotometer, and you can look at different solutions sequentially without having to keep on changing the setup. So there's different variations on a theme, but this is the basic operation of a spectrophotometer. Right, so what we're going to do now, folks, any questions on that before we actually move across to Thomas to make a measurement?
No questions from me.
That's fine. Thank you.
All right. That's the problem now with scientific instrumentation. Everything is all beautifully boxed up, and that you don't get a chance to see what's going on inside the instrument. And you know, this stuff here, that's far more interesting than having a big white box or grey box outside it and pressing buttons. But of course, it's got to be enclosed in this case for two reasons. One is you don't want any stray light getting into the instrumentation, and two, because of safety. There's all sorts of electronic components inside here and high voltages, so it's not safe to leave something like this exposed, particularly for general users. So the encasement of instrumentation, especially those which involve lasers and things, this one doesn't, is now an essential part of health and safety regulations and the safe operation of scientific instrumentation. But even a simple spectrophotometer is, I think, a useful piece of instrumentation. Right, so now we're going to move to laboratory A17, and that will be Thomas. So let's just have a Vlad, can you switch over now to your phone? Okay. Can everyone see you? Can you all switch to Vlad now? So spotlight, Vlad.
Can you all see me now? Yeah, you see me, Thomas? Do you see me? Yep, you must be able to see me. That's me there.
Well, we're getting echoes. That's probably because I'll put myself.
Swap it. It's a little button there that says like swap camera. Yeah, I know.
What you see now is Thomas. Vlad, you shouldn't be there for very long because of the social distancing. Hand over to Tom straight away. Over to Thomas.
Hello, yes. So here is the spectrophotometer that we're going to be using. You'll have to tell me if you can see this okay, because I cannot see it on my phone screen. It is far too small. Okay, so here we have the cuvettes already in place. So in position 1, we've got one that's just filled with our solvent. And in position 2, we've got one that's filled with a solution of evalvamin. So you can see you've got to be careful to get the clear sides, so it'll be in the path of the laser. And as I think Steve mentioned, this spectrophotometer will this part will turn, so we don't changing the cuvettes between each reading.
And one sample is the blank, is that right, Thomas?
Yes. So yeah, we'll rotate between the blank and the sample you want to measure each time. So if I just press on here, can you see the screen okay?
Yeah.
If I just press run, and it will measure the absorbance. So the first one it will measure is that first cell 1, which obviously it isn't anything useful, it's just a blank, so this should come out as 0. If it doesn't come out as 0, then I know there's a slight issue, and I'll have to try and fix something.
So this is a blank just containing the, what is it, phosphate chloride buffer? What's in the what's the reference?
Yeah, so just phosphate chloride buffer as we normally use in these labs. So yeah, it's coming out as 0. Means everything's working okay. So if I press run again, actually I think I can show you the inside. So you can see it's rotated, and now here in the path of the laser is cuvette number 2.
Which contains your solution, yeah?
Yeah, so if I now press start, it will measure the absorbance of that solution of albumin.
Which is what the concentration we want to find, yeah?
Yes.
Okay, it's thinking about it.
Okay, so that's given us a value of 2.641. But unfortunately, that's too high. So ideally, for absorbance measurements, you need it to be below 1.2. So what I've also done is prepared a solution of albumin which has been diluted. So it's been diluted 11 times. So I've taken 1 milliliter of the albumin and put it in 10 milliliters of the buffer.
You mean it's been diluted by a factor of 11? Yeah. So you've added
Yes.
10 mils of phosphate buffer to 1 mil or whatever of the solution. Yeah, great.
Yeah. So then, so I've put samples of that diluted solution into the next 3 cuvettes, so numbers 3, 4, and 5. So if I just press, basically if I press run 3 times and wait, then I'm going to be able to see 3 values for the absorbance, which should be in a range you can measure, and then you'll be able to take an average of those readings and find what the concentration of the albumin solution is.
Okay, so these are all which have been diluted by 11, not the whole sample, just a aliquot of it, so you can make the absorption measurements. And these should hopefully come in within range of the Beer law now, which is less than 1.2, or I think 1.4 maximum really, but preferably below 1.2. Let's see. There we are, look at this. So
Number 1.
yeah, just to lower the camera a bit, Thomas. Yeah, we've got 604, yeah. And that's just doing, so what you've done, Thomas, is you've done
Yeah, so there's 3
solutions.
separate cuvettes, so we'll have 3 values, so we can find an average, so it should be hopefully more accurate than just taking 1 reading.
Absolutely. That just also checks that you haven't made any errors, basically, so if you can do it 3 times, that's great. It's just doing the next one, 603. That's pretty good.
So we see they're pretty close together, so hopefully that means there's not any issues.
This is great. I mean, we could have done it pre-recorded, and then we could have got rid of all the little problems that we had in terms of screen. But this is fun.
Okay, so we've got 3
It's a
readings.
bit lower, that. Yeah, that's a bit lower.
Can you see those okay? It's looking a bit blurry on my phone, but can you read the numbers? So if you write those down and take an average, and then we'll have a little break while I come out of this lab, so Vlad can come in and do the next bit, and you can calculate what the concentration will be.
Yeah.
But just remember, this is the diluted sample, so you don't have to multiply whatever you get by 11 at the end.
Thanks, Thomas. Yeah. So what we'll do now, have just a 10-minute pause. And for us, we're having a pause, not for you guys. So what you've got to do now is you've got to use those values that you've measured with, or Thomas has measured. I think it's reasonable to take an average. It's tempting to ignore that third data point because it's a bit below the others, but it's not that different really. So take a mean of values and then use the equation which I've given you, the Beer-Lambert law equation, A equals epsilon LC. The path length, Thomas, was 1, is that right? Yeah, Thomas has gone, but the path length is 1 centimeter. You've got the average absorption value. So if you can work out what the concentration is after allowing for the 11-fold dilution, and we'll reconvene. Well, no, I think we'll reconvene at 10:55. Okay. So if you can just do those calculations now, and then we'll see what we get. Hopefully we'll get the same answer.
Steve, I have a question, please.
Yeah, sure.
I have seen on the screen that the lambda were 280. So why we have choose this? Why we haven't 260 or 270?
Right. Does anybody else know the answer to that question, Khalil?
Isn't it based on the absorbance of light the cells that we're checking can absorb?
Yes, that's right. And what's the wavelength that most proteins absorb at? Why do we set when we're making measurements on proteins, why do we normally set the wavelength to 280 nanometers?
Because most of them absorb it between 200 and 280.
At 280, but why 280 nanometers in particular?
Aromatic rings, isn't it?
Yes. The tyrosine and tryptophan groups.
Yeah, tyrosine and tryptophan. Yes.
An absorption maximum at 280 nanometers. That's why we work at 280, Khalil.
Thank you very much.
Oh.
So for proteins which don't have any tyrosine or tryptophan, would you still measure them?
Say that again.
Proteins which don't have any tyrosine or tryptophan residues, would you measure them at 280 still?
So if you don't know what the absorbance is, what you can do is measure the peak. So you do like a wave scan for whatever material it is. You identify what's the peak absorbance, and then you can use that.
Okay.
But usually most proteins will have it.
Thank you.
Right, put the box back on. How are you doing, folks? Have you got it sorted yet? Yeah. Doesn't look as if Vlad's looking very well at the moment. Vlad's turned into a very blurry lamp by the looks of it. Oh no, he's moving in. Right, raise your hands, folks, when you've worked out what the concentration is. And don't forget to correct for the dilution. Thomas, what was the concentration? What was the concentration? Yeah, I'll do it now myself. Sorry, what's that? Right, let's get a pen. I'll just check the concentration myself, then we'll move on to you. Glad we want about 2 minutes, okay? Do you need a calculator? No.
Steve, I think you are mute.
Okay, guys, just to don't forget, raise your hands when you've worked it out.
I have put the answer in the chat box, Steve.
Okay. What's do. 601. So C equals A over E lambda L equals 601 divided by 660. 9 minus 4 times 11 equals 0.010 grams 010.0 gram per mil equals 10.0 meg per mil. Let's see what we get then on chat. Come on. Right, just check your chat answers. Right, what have we got, folks? That's not correct. It's did you anyone else got some answers, folks? Because don't forget to multiply by the correction factor. Amber, George, Mohammed, Khalil, Victor. What do we get?
Well, for the second reading, the 2.641 absorbance, I also got 0.103 grams per mil. So I guess I've done something wrong.
Yeah.
Steve, I want to double check about the protein, which is ovalbumin, yeah?
Yes. The extinction coefficient is 660 mils per gram per centimeter.
Oh, it's 60. Wait, the extinction coefficient is 660, not 280.
According to the sheet here, it says 660. Yeah.
Oh, I thought we said 280 earlier, so I was using
No,
280.
the wavelength is 280.
Oh, okay. Okay, that's where I've got it wrong then. That's where I've got it wrong. Is it 0.044 grams per mil?
No.
Huh?
Thomas, what was value you got? I got 10. All right, it comes out. I'm afraid not, Khalil. Come on, folks. Amber, George, Mohammed, Victor.
I'm sorry, my Wi-Fi keeps cutting in and out, so I can't see any of the numbers.
Right, so I'll give you the readings, okay? The readings for the absorbance were 0.603, 0.604, and 0.597. So the first thing you have to do is take a mean of those three values. Okay, what do we get for the mean value for those three absorbance readings?
0.601.
Does everybody else agree? Khalil?
I have got right now 0.889.
No, that can't be right. For the absorbance, what I'm asking for now is what's the mean absorbance value? You've got three values, 0.603, 0.604, and 0.597. We want to know what the mean of those three values is.
0.601.
Yep. Amber?
Yes. Steve, I have a question. Why we have to choose just 3 samples out of 5 samples?
Who asked that question?
Yeah, Khalil. I'm Khalil. So why we have choose just 3 samples out of 5 samples?
Because those 3 samples have had the 11-fold dilution. We can't choose the value which gave 2.6 because it infringes the Lambert-Beer law, which has a maximum value of, what do we say? The maximum value for Lambert-Beer?
I think 2.641.
No, that's a reading. What's the maximum value of the what's the limit? 1.4, yeah, 1.2 to be safe, 1.4.
I got it.
So we can't use the 2.6 value because it's beyond the Lambert-Beer. That's why we've had to dilute by a factor of 11 to bring it within the Lambert-Beer law, and 0.6 is within the or 0.5. All those 3 readings are within the range of Lambert-Beer.
Yeah, I got it. Thank you, Steve.
All right, folks, so 0.601 is the average. Do we all agree with that?
Yes.
So
Yeah.
all we have to do is to...
You got to divide it by the 660.
Yes, we just got to rearrange that equation. So concentration is absorbance divided by the extinction coefficient times the path length of the cell. And the path length of a cell is
1
centimeter. That's okay. And the extinction coefficient is
660.
So it's that number divided by 660.
Yep.
And that comes out to be?
Gives 9.1 multiplied 10 minus 4, yeah.
Yes. And that's in units of grams per mil.
Mm-hmm.
But what must we do? That corresponds to the 11 times diluted sample. So what must we do to that number?
multiplied by 11.
Yeah.
multiplied by 11, okay? And it comes out to be 0.010
Yeah.
gram per mil, not 0.10, 0.010. So I think you made a mistake there. 0.010 gram per mil. And to convert to milligrams, how many milligrams is 0.010 grams? How many grams in a gram?
10 or 10 minus 3. 10 minus 3 milligram equal 1 milligram. Or sorry, plus.
5,000.
1 milligram. So 1 gram is how many milligrams?
10,000.
No.
Sorry, 1,000.
1,000.
Yeah.
1 gram is 1,000 milligrams.
Yeah.
So we must multiply 0.010 by 1,000. And what do we get?
Ten.
10. Okay. 10.0 milligram per mil. And Thomas tells me he made up the solution to 10.2 per mil approximately. And when you make up a protein solution to a concentration, sometimes there always is water bound to the protein anyway before you start to dissolve it in solution. So that when you measure the protein concentration, it usually comes out less than what you think it is because of water that's already bound to the protein molecule before you put it in solution, because proteins absorb water vapor from the air and things. So 10 mg per mil is a very reasonable value. And when making calculations, determinations of this sort, always look and see if the answer makes sense. All right, so what's come out of that is be very careful when you're doing your calculations, and be very careful when you're doing your conversion factors, from grams to milligrams, liters to milliliters, this sort of thing. All right, folks, any questions on that before we move on to Vlad's bit? Amber?
No, perfect, but thank you, Stephen.
Okay, Amber, you happy with that? Amber? I think we lost Amber. George, okay with that?
Yeah.
Mohammed, okay?
Yeah, I'm fine with that.
Khalil, yep.
Yeah, it's perfect. Thank you, Steve.
Fine, okay. Well, we'll soon find out if you got that, because in the assessed questions, I think the first two involve some sort of calculations like that, and one's involving a dilution. So we'll find out if you've understood it. But just ask any questions if you didn't get that, didn't understand what we were doing there. And the important thing is 280 nanometers is the wavelength, not the extinction coefficient. We work at 280 nanometers because that's where all proteins absorb, as long as they have aromatic residues like tyrosines and tryptophans. Great. Right, so I'm going to hand you over now to my colleague Vlad, who's just going to show you a refractometer. There's no need to do any calculations on this, just for comparison to see what we can use it for. Just let me know, folks. Why would we want to use a refractometer for measuring concentration? What's the big advantage of a refractometer for measuring concentration compared to a spectrophotometer?
Maybe it might be used to measure the viscous solutions.
Well, we can measure we can measure viscous concentrated solutions. That's correct. But what's the main advantage of using a refractometer for measuring concentrations of molecules?
Or we can use it for the absorbance more than 1.5.
Yeah, we can look at higher concentrations, sure. But what's the? You mentioned absorbance there, Khalil. We don't actually measure absorbance with the refractometer. We measure the refractive index properties. But what is it about? I mean, we mentioned proteins have aromatic groups which absorb in the ultraviolet. What don't other molecules like polysaccharides have? Or carbohydrates? Well, they don't have these aromatic residues, so we can't use a spectrophotometer for measuring the concentration of carbohydrate solutions because they don't have anything which absorbs UV or visible light. So we can't use a spectrophotometer, as you just done. Instead, we can use a refractometer because whereas only certain molecules like proteins, nucleic acids absorb light, ultraviolet light, all macromolecules will bend the direction of light. This is called refractometric properties, the ability of a material to bend the direction of light. So all macromolecules of the polysaccharides, proteins, nucleic acids will bend the direction of light depending on how concentrated they are. So the more concentrated solutions are, the more the direction of the light is bent. And that's what a refractometer measures. And that's what Vlad's going to show you now. He's going to show you a refractometer, which is used for measuring concentrations based on the bending properties of light. Right, Vlad, over to you.
Okay, thank you, Steve. So as you guys can see, this is a refractometer. It's got a reference channel and a sample channel. So of course, when the light passes through, the refraction happens.
Vlad,
And of course, the sample is going to, yeah.
just show us a distance view of the refractometer first of all, so we can see it.
Yeah, is that okay? Can you guys see that?
Yeah. So it's much smaller, a bit further away. It's much smaller than a spectrophotometer. Yeah, it still costs the same money. It still costs you a few £1,000s, but it's a much smaller instrument. Thanks, Vlad. And we're not using cuvettes now, are we?
No, we're not. So we're just injecting it with a syringe. We have the buffer and the sample. And of course, the changes in refraction will be recorded. And after we zero the instruments, it will give us a reading, which is in bricks. And this machine works in relative to the sucrose. Should I go through this as well, Steve? So
yeah, just show that. They've met this in the lectures. It links the concentration with the difference in refractive index N of a solution between that of the solvent, which is water normally, or phosphate chloride buffer or whatever, which is N0, divided by not the extinction coefficient this time, but something like the extinction coefficient, which is called the DNDC. Sorry, Vlad, you've gone off it. To show that equation again.
Yeah.
Which is the same as a bit further out, bit further out, Vlad. which is the same as the factor R, which we gave you in the lectures. So for proteins, it's about 0.19 mils per gram, and for carbohydrates, it's about 0.15, 0.16 mils per gram. And yeah, all the values are in this wonderful refractive increment data book. Very pretty picture.
And we can find for albumin exactly as well.
Yeah. So what value is
buffers? So we have 1.88.
Hang on. No, 0.187. 0.188.
So 0.188.
Yeah, or 18. Yeah. Okay. Depending on the temperature and conditions. Yes. Mils per gram. Yeah.
Actually, this one, it says it was 0.5 degrees.
Yeah, it depends on temperature. There is some temperature dependence.
It's slightly lower. If we go for 25 degrees, it's 0.182.
Okay, but it's of the order of 0.18, 0.19 mils per gram, which is an average value for a protein. Excellent.
So we usually, how it works, we usually just zero we blank it, just like we did with the spectrophotometer. So that's where you have the buffer in both channels.
Yes. And then you take out the buffer out the sample channel.
And we inject it with the solution.
With a syringe, or what are you using?
Yeah, so for this one, we're using a 1 ml syringe. Sorry, I need to...
The wonders of live broadcasts.
So yeah, we have this of albumin. We're still waiting for the zeroing.
Okay. Now you guys did say you'd like a live broadcast, didn't you? I did ask you the question. Okay, so how much? It's about 1 mil. How much are you using, Vlad?
Yeah, 1 ml is enough.
And this time, there's no need to dilute like with a spectrophotometer. You can just put.
Well, yeah, it has an upper limit actually of what is it, 2% or something like that, which means 20 mg per mil.
That's 20 mg per mil. That's very, very high.
So it's very, very high indeed. Yeah. So now it says it's finished the zeroing, and that's fine. We go back to entry, and we can either check by pressing start to make sure it's 0, but it's probably 0. But I'm not going to do that. Instead, I'm just going to inject some solution just very slowly. We could also recover it. If it's very precious sample, we can recover it from there.
Can I say, folks, that Vlad's doing a tremendous job here, as did Thomas, because of the COVID restrictions. Only one person is allowed in the laboratory. So that means no one there to hold the camera. So Thomas and Vlad have been operating with one hand, whilst the other hand is holding the camera mobile phone. So that's incredible, really. That's why things are moving around a bit.
So basically how this one is going to work, we have the instrument will give us a value of bricks in percentage, which roughly translates to grams per mil if we divide it by 100. But then, of course, we can also take into consideration the DNDC value. So in this case, we're using the DNDC of the albumin. And we also have this calculation here where we divide by the DNDC of the sucrose, because that's how this particular instrument works.
Yeah, this instrument is set up for, the instruments are usually set up with an industrial bias, and the refractometers are commonly used to measure the concentrations of, in the food industry, for example, the concentrations of sugar solutions. So This bricks thing refers to carbohydrates, where it does things automatically. For protein work, of course, we're not working with sugars, so there's a simple conversion involving the refractive increment value for sugars and protein molecules. So that's just a peculiarity caused by the industrial bias of this particular piece of instrumentation. But since most of you, apart from Amber, are doing the industrial physical biochemistry course, that's something which is worth knowing. Anyway,
So in this case, we have a value of bricks of 0.13, which according to this formula here, if we roughly divide it by 100, we get a concentration in grams per mil, right?
Yes.
And if we want mgs per mil, it's actually multiplied by 10. So it's a 1.3 meg per mil.
You multiply the bricks value by 10, not the mig per mil, not the gram per mil value.
Yeah, of course. So you multiply the bricks value by 10, which is this one.
Yes.
And we get a value of 1.3 meg per mil.
Right. Okay, that's different from the, was that the diluted Thomas sample you were looking at?
Yeah, so that is slightly different from the spectrophotometer, and I think that is because there's other things in there, I think, which don't absorb. Is that true?
Yeah, that's right. Yeah. So that will tell you the concentration of all the material in there. Okay.
Yeah, well, I think that's enough. That's it for me. I mean, you can clean it now, and that's it.
Fine. So this solution was different from what Thomas looked at.
I think it's the same solution, Thomas. I think it's the same. Yeah, it's the same. It's the in 11.
Dilution. Okay, that's fine. Yeah.
So yeah, it's the same, and it gives slightly different concentration reading
Because of the other material in there. Yeah, okay, that's fine. It's not too far away from the value we got for the spectrophotometer, and then of course we multiplied by 11.
And of course, we haven't done actually this, Steve. We haven't done this because if we divide 0.19 by 0.15, that would bring it down a little bit more, I think, closer to that of the spectrophotometer.
Okay, that's fine. That's fine,
So,
Vlad.
yeah, it should be about the same.
Yeah. Okay, thanks, Vlad, for that, and incredible work where you're using one hand.
Yeah.
With the camera.
Back to you now, Steve.
Heroic efforts. Okay, folks, so now you've got an idea what a refractometer looks like and a spectrophotometer, and you've seen inside a spectrophotometer and how these scientific instruments operate. They're not just a big box with magical things inside. They are precise optical instruments, and that's why I always like taking the front end off things. With them switched off, of course. You can't do it with them switched on because of health and safety regulations. Great. Sorry, folks, it went a bit longer than I'd anticipated. We've gone an hour and a half, but is anyone happy with that?
It is really amazing lecture today. I'm happy with that, yeah.
All right, the most important thing is doing those calculations and getting those numbers right, though. And it's been very useful doing that exercise today because we found out how to use extinction coefficients correctly, how to take means correctly, how to change from milligrams per mil, sorry, from grams per mil to milligrams per mil by multiplying by 1,000, and understanding that the extinction coefficient is not the same as the wavelength, and then seeing how for any macromolecule, we can use a refractometer, whereas for proteins, nucleic acids, which contain absorbing chromophores, because of the aromatic groups, we can use a spectrophotometer. But if the reading is too high, we have to take a small sample away and dilute it, measure the absorbance, and then remember how much we diluted by to get the correct concentration of the original solution. Great. Amber, are you okay with that?
Yeah.
So you should be able to do questions 1 and 2 now on those assessed questions. With the MRes group, we're going to meet you again at 2 o'clock, folks. All right?
Yeah.
Yep.
To discuss the projects, industrial placements, and what we have planned for you, and what needs to happen between now and next January, when we start to do the research work. But we'll describe all that at 2 o'clock when we see you then with Judith. And the date for the not the Secret Santa, we can't do that this year, but the date for the seasonal sing-song is going to be on the Friday, the 18th of December, last day of term, at 4:30 p.m. But we'll tell you more about that later. And Amber, if you want to join us, you're very welcome to. There'll be other groups as well joining in, where we have some festivities. Again, it'll be online this year, but it'll still be great. Fab. Thanks, Amber, and we'll see the rest of you at 2 o'clock.
See you, Steve.
Thanks,
Bye.
Steve. See you too.
See you too.
Bye, Steve.
Thank you.
Bye. Bye, Kesha.
Bye. Steve, do you have any pointers on question 9?